Hello, statisticians. Just a quick run through here of the three partner test FRQs. So first one, number 17 here, if you haven't read, a laboratory test for the detection of a certain disease gives a positive result 5% of the time. For people who do not have the disease, the test gives a negative result 0.3% of the time for people who have the disease. Large-scale studies have shown that the disease occurs in about 2% of the population. So as you think about this question, first of all, in these false positive, false negative sort of situations, a good way to start is with a tree diagram. And so we look at this in terms of um, who has the disease. So if I look at this as disease, who has the disease and who doesn't? And we know that 2% of people have it and 98% of people do not have the disease. And then we look at testing positive versus negative. Okay, so this is the test, positive, negative, positive, negative. Okay, so for people who have it, 0.997 or 99.7% of the time they test positive, and 0.3% of the time they test negative, as it says in the question right up there. And then it says laboratory tests for the detection of a certain disease gives a positive 5% of the time for people who do not have it. So that means this is 0.05 and this is 0.95, which again, for the 98% who don't have it, 5% of those folks test positive. So as we'd like to do, we're going to go ahead and get these probabilities fleshed out here. Let's see, that's 4 zeros and then a 6, 0.049, and 0.931 would be the overall individual probabilities of these events occurring. And so another way of looking at this, I'm just going to use the thousandths place, is let's just say we've got now people who have the disease over here and people who test positive or negative here out of, let's say, 1,000 people overall. So this positive would mean that about out of a 1,000 people, that we would get about 19.9 who would be in this group. So about 20 individuals would have the disease and test positive. And again, I'm just moving this over 3 decimal places because now it's, instead of being out of 1, it's now out of 1,000. And so it's like we've moved this over 3 decimal places. So moving the next one over 3 decimal places, I still only have 0.06 of folks who who have the disease but test negative. So there'd only be 0.06 people in that situation. There would be 49 people who do not have the disease but test positive, and 931 people who are negative. So again, all I've done is I've taken the probabilities that we have here and I've just converted them to closer to whole number values. I could certainly move this over another 2 decimal places, so I'd get 6 in the top right rather than 0.06, but this gives me another way of looking at this. And again, as we go down here, we would expect this number, let's see, this number here to be 980 roughly. This would be 20 roughly, even though it rounds out a little higher than that. And that represents the 2% out of 1,000 who have the disease, and the 98% out of 1,000 who do not have the disease. So just converting it for ease. So when you look at the first question here, what is the probability that a person selected at random would test positive for the disease? Well, the people who test positive here are these two groups, or as we look at this, these two groups here tested positive. So to test positive, okay, so if we look at part A here in the question, now that we have all this data and all this information, the first part is just asking, what's the probability that somebody tests positive here, which would be really the probability that somebody has the disease, so disease positive, times the probability that they tested positive given that they're disease positive, plus the people who don't have the disease, who are disease negative, times the probability that they do test positive even though they're disease negative. So what that is just a run through of the table here or it's this group here, which would be all of our test positive group. And so when we look at this, the run through of the table on here of the tree diagram, here's our test positive groups. And so we already know that the first group that was disease positive and then tested positive given disease positive was 0.01994. And the group that was disease negative that tested positive was 0.049. And so it turns out that the probability of testing positive, again, I probably should have written test positive here, that probability would be 0.0689 about. So that gives you the probability that somebody tests positive. And again, you just have to worry about both scenarios. And again, the tables allow you, I wrote the full notation here, but the tables do allow you to work through that a little more shorthand. Part B here, what is the probability that a person selected at random who tests positive for the disease does not have the disease? Okay, so now what you're really looking at is the probability, here, let me just separate this out. So the probability that somebody is disease negative given that they actually tested positive. So in this situation, you're looking at really the probability that somebody was disease negative and tested positive over the probability that somebody tested positive. Okay, so when you look at this one here, you can look at the two-way table and see on the two-way table about how we have this is 68.9. These are out of all the folks who tested positive, how many of those people did not have the disease? So in this situation, that's really the 49 out of the 68.9. Okay, so that's if you look at this, these are of all the people who have tested positive, who doesn't have the disease, which again is just another way of looking at this. If you look at the numerator here, and we go back to the tree diagram, disease negative and positive is this group. So let me switch the colors here. That would be this group was disease negative and tested positive, which is up top. Then you look at everybody who tested positive. Everybody who tested positive was actually these two groups right there. So there's your denominator. So this would be equal to 0.049 over the sum of 0.01994 plus 0.049. So that would be our overall percent chance. And again, if you're using the diagrams, you may not think of it like this, even though this is from our formula sheet with the A given B or B given A on our formula sheet. So this here should end up being, let's see, 49 divided by 68.9. This is about a 0.7112 or so probability. So this is a great question to look at tree diagrams and two-way tables. Let's go on to what would be number 18 here for us. So 18 starts off with a straight two-way table here. We are given gender and party, a political party of some sort here. And so the first question here, what is the probability, given that a registered voter is male, what is the probability that they're party Y? So this is party Y given male. So again, you got to worry about that notation. And when we look at this, given that you're male, well, there's 200 males, how many of those males are in party Y? Would be 48. So this is a 0.24 or 24% of the males are in party Y. Now, part B, among the registered voters, are the events male and is registered for party Y independent? So when you look at this, you think about, if I look at this as gender as the cause and party as the effect, for instance, then I would be looking at, is party Y independent of the idea of being in party Y given that you're a male? So effect given cause there, really. Well, we just answered the second part of that above, and if I had space below this, I'd write it there. But so this part is 0.24. Now the probability that somebody's in party Y here, change colors just so we can see this a little easier. Party Y is 168 out of 500. So I'll put 168 out of 500 there for now to convert that to a decimal so that people can see it a little easier. But this would be then, does 0.336 equal? Again, these are all question marks here. But does that equal the other side of this, which is 0.24? Of course it does not. So therefore, in this case, you're being a male and party Y are not independent of each other because these scenarios are not equal. So I would say because party Y does not equal party Y given male. And again, what we're showing there simply is for the general population, about a third of the general population is in party Y, but amongst males only, about 24% of males are in party Y. So being a male clearly affected one's probability of being in party Y. Specifically here, the chance of being in party Y went down if you were a male, which means, of course, for females, the percent who were in party Y was higher than that 33.6. And specifically here, 40% of females were in party Y. Okay, so the party Y was 33.6 total, and it was actually broken up as 24 and 40 by gender, which clearly means gender is playing a role in being in party Y. Now, for the third part here, they give us the breakdown, and here again is that party Y breakdown, many more higher percent of females than males. So here's our 0.4 and here's our 0.24. Okay, and we could figure out the rest of these, what percent are party X females and what percent of males are party X and so forth. In fact, I'll just quickly, this is also 40 and this is 20. For the males, 14% were in party W and about, 62% were in party X. So you can see the breakdown here is different by gender. And in part C, they're asking us to redo this graph as if the genders were completely independent. So what would happen is if gender was completely independent of your political preference, then we'd look at party W and say that overall 88 out of 500 people were in party W, which means 17.6% of the population was party W. So we'd go down here to about 17.6, and this would be party W. Okay, those would both be 0.176 because again, we'd be saying it's independent. So if 17.6% of the population was party W, then if gender didn't matter, it would be 17.6% of males and 17.6% of females. Okay, for party X, which we saw 40% of females were party X and 62% of males. Well, overall, that number was 48.8. And so we'd go up to about, when you add these up, it's about right there. These would be party X, and that's 0.488. And so combine those two, add up to about 66.4%. Excuse me. Which means the remaining folks would be party Y, and party Y then would be the remaining 168 out of 500, or 0.336, which is what we found already up in part A up there in that independence question. So this is what the graph would look like if gender didn't play a role in your political preference. It would just be the top half would look exactly like the bottom half. It doesn't matter that we have 300 females and 200 males in this sample. It just means in this part that the female percentages had a little more weight to them because it was 100 more people in those. But ultimately, when you got down here, yes, those averages overall ended up being a little closer to the female numbers. But what we're looking at is just what percent in general came from each party. So that's what this graph would look like if things were truly independent. So this would be like a p-value of 1 if it were a chi-square down here, and we could do the same thing and run a chi-square test for independence to see, are these percentages off enough from what they were in the bottom? Okay, like is 20 and 14, is that far enough from 17.6 in order to actually reject and say that gender is statistically significant in this case in terms of its effect on political preference? But we know for sure that they aren't perfect, and that's exactly what, sorry, I said part A earlier. That's exactly what part B showed us, that party Y is different by gender. So we'll leave it at that for 18, and let's end here with number 19, which is a straight two-way table. And this is an old AP exam question, as were the last two. What is the probability that a person chosen at random from this sample will be 31 to 45? So this is 31 to 45. And we would look here at 31 to 45 as the 89 out of 207. Okay, big piece here is you need to include this notation so you can tell the reader what you are including here. But that would be approximately 0.4300 when you round up in this situation. Okay, so that would be A, the probability that somebody is 31 to 45. Okay, part B here. What is the probability that a person chosen at random from the sample whose income is over 50,000 will be in this category? So now you're saying, what's the probability of 31 to 45 given that your income is 50K plus, which in this situation, that's the biggest income of them all. So it's basically that you're in the second youngest group, but you're already making over 50K in this suburb. So again, when we read this, what is the probability that a person chosen at random from those in this sample whose incomes are over 50,000? So that just tells us, that means we're talking about the 96 people who are over 50,000. So that's the given 50,000 plus. How many are in that age category? Oops. And that is 35. So 35 out of 96 means that about 36 0.46 or 0.3646 is the probability that somebody is 31 to 45 given that they're in that age group. Given that they're in that income bracket in this case. So part C, is annual income independent of age in this situation? And in this case, A and B answer the question for us. Okay, so to see if they're independent, we are just checking, does the probability of being in the 31 to 45 age group get affected when we start to break it down by incomes? And what we found is 43%, or 89 out of 207, are in that 31 to 45 age group. But if you now just look at the people making over 50,000, only about 36 or 37% of those are in that 31 to 45 age group. So the income did play a role in the breakdown of the age groups. Namely, you'll see that income, that the income was higher with older population here, and so your age did play a role, just like it would in something like marital status, where your age would play a role if you're single or married, widowed, divorced, and so forth. So again, we would say because these two are not equal, because probability of 31 to 45 does not equal the probability of 31 to 45 given the 50K plus, we know that age and income are independent, or not independent, sorry. We know that age and income are independent of each other. In other words, what we're seeing here is that your income did play a role. We will leave it at that. Notice that this is actually kind of effect and cause in this one. It probably makes more sense if it's income based on your age, but this is how this question was set up, and it is allowed to be this way here. And so what we're seeing is the effect then that income had on your age, or that income did change the breakdowns of age, I should say. And so you just use A and B. Alrighty. If you have any questions, please make sure you ask, but those are the 3 FRQs from the partner test. Thank you.